Hi all. So once again welcomes to the channel, and we are discussing the portions from linear control system subject, and today we are going to discuss about the concept of stability of a system. How we can define the stability. Okay, how we can find a system is stable or not. Okay, so in simple words we can define stability as, that is, suppose if you are having two ports. Okay, if you are having two ports which are placed like this. Okay, and if you are having two balls, okay, you are going to place that balls in these ports. Okay, so one ball is placed like that. The first port we have placed the one ball like that, and in the another port we have placed the one ball like that. Okay, so these are two systems. Okay, this is system 1 and this is system 2. Okay, in the first system, if you are applying any force area or any disturbance in this ball, okay, if you are applying any force or any disturbance in this ball, we know that the position of the ball is changed. That is, the characteristics of the system is changing. Okay, so about in the case of second, okay, in the second case, if you are applying any force or any disturbance, we know that the ball of course will back to its original position. Okay, until if we are applying a force that is capable to throw this ball out of the spot. Okay, it's another case, but in normal case we can say that if you are applying, okay, if you are applying a force, okay, a force on this ball, the ball of course regain its original position. That is, the characteristics of the system is not changing. Okay, so we can say that this is a stable system, but here it is an unstable system. Okay, so that is the stability. Okay, and the stability refers to the stable working condition of a control system. Okay, stable working condition of a control system. So every working system is designed to be stable. Okay, so in a stable system, the response or output is predictable, okay, finite and stable for a given input. Okay, or for any changes in input or for any changes in system parameters. Okay, so in the cases we can predict the output and finite and stable, okay, for a given input. So a system is stable if its output is bounded for any bounded input. Okay, bounded means its output is finite. It is not infinite, it is finite. Okay, so the output is finite for any finite input, that is bounded. So bounded input, bounded output. Okay, so that is the case of a stability. Okay, so the systems may be stable, unstable, marginally stable, like that. So we will discuss it later. So before that, we must know what is the impulse response. Okay, impulse response of a system. Okay, so normally this impulse response is very important. Okay, important in the case of stability, because the output of a system, okay, the output of a system for any arbitrary input, okay, for any of the input, can be obtained by taking the convolution of the input and this impulse response. Okay, so that's why this impulse response is very important. Okay, so let's have a look at the impulse response of a system. Now we know that the term M of S denotes the closed loop transfer function of a system. C of S is the output response and R of S is the input, and we know that M of S equal to C of S by R of S. Okay, our normal equation. And the response can be written as C of S equal to M of S into R of S. And in time domain, we know that the response in time domain is C of t. C of t can be found out by taking the Laplace inverse of the C of S. Okay, C of t is equal to L inverse of C of S, and also the R of t. Input in time domain is also equal to R of t equal to L inverse of R of S. Okay, and if you are taking for an impulse input, okay, we are taking R, okay, R of S as 1 here. Okay, for an impulse input, we know that R of t is delta of t, and the Laplace transform of this R of t, that is R of S will be 1. Okay, so that is the impulse input. Okay, so for that case, what will be the response? Okay, so the impulse response, that is L inverse of C of S, that is C of t will be, so we have to take the Laplace inverse of C of S. So it means we have to take the Laplace inverse of this M of S into R of S. Okay, that is Laplace inverse of M of S into R of S, and we know that the R of S is 1 for impulse response case. R of S is 1, so L inverse of M of S, which give M of t. Okay, which give the M of t. Hence the impulse response, okay, the impulse response of a system is the inverse Laplace transform of system transfer function. Okay, that you can see here. The impulse response of a system is inverse Laplace transform of system transfer function. That is, if you want to find, if you are asked to find the impulse response, okay, then we have to simply find the Laplace inverse of our closed loop system transfer function, that is M of t. That's our impulse response. I have already said that the impulse response is very much important in stability, determining the stability. So here the response, okay, the response C of t, okay, as in the definition. Okay, so the response C of t can be found by taking the convolution, okay, convolution of M of t and R of t, okay, where this star symbol is the convolution, and mathematically we can write the convolution operation as C of t is equal to integral minus infinity to plus infinity M of tau into R of t minus tau d tau, where tau is the dummy variable used for integration. Okay, so the output of a system for any arbitrary input can be obtained by taking the convolution of input and impulse response. So this M of t is very much important. Okay, so by observing the M of t, we can say whether the system is stable or not. Okay, and one more thing, the bounded input and bounded output stability, that is BIBO stability. So it's a very much important thing. Okay, BIBO stability. So a linear relaxed system is said to have BIBO stability if every bounded input, that is finite input, results in a bounded output, that is finite output. Okay, then we can say that it have BIBO stability, that is BIBO, bounded input bounded output stability. Okay, and the condition for BIBO stability can be obtained from convolution operation of this one. Okay, this equation. So we can simply write the equation as response C of t is equal to integral 0 to infinity M of tau R of t minus tau d tau. Okay, so here the integration value is 0 to infinity here, but in the early case it was minus infinity to plus infinity. Okay, the reason why, because a relaxed system, so it is a relaxed system. A relaxed system is one in which the initial conditions are 0. Initial conditions are 0, hence the limit of integration is from 0 to infinity. Okay, so this is the mathematical representation of BIBO stability. So next we are moving to the location of poles on S-plane for stability. Okay, that is, by observing the location of poles in S-plane, we can say whether the system is stable or not. Okay, so we know that for a transfer function, we are having a transfer function like that. Okay, that is M of S equal to C of S by R of S. Okay, we know that the numerator will be a polynomial and denominator will be a polynomial, and the roots of the numerator polynomial are called as zeros, and the roots of denominator polynomial are called as poles. Okay, this is the roots of denominator are called as poles. Okay, so the poles, the location of poles may be at origin, and it may be lying on imaginary axis and it may be lying on right half of S plane and left half of S plane, like that. Okay, so based on that we can determine the stability of a system. Okay, so these are some examples. That is, in the left side column, the trans function m of s and location of roots on S plane is given, and in the right side we are having impulse response m of t. That is the Laplace inverse of the closed loop trans function m of s. That is m of t. We know that m of t is the impulse response. That is Laplace inverse of closed loop trans function represents our impulse response m of t. So by observing the m of t, we can say whether the system is stable or not. Okay. So here the first trans function is like that. That is a by s plus a. Okay. So here we know that the value of s will be is equal to minus a. Okay. So the pole. Okay. The pole is located in the left half of S plane. That is, you can see here, it is located in the left half of S plane. Okay. So which means roots on negative real axis. Okay, root is on negative real axis, and if you are taking the impulse response m of t, that is Laplace inverse of a by s plus a. We know that the Laplace inverse is a into e raised to minus at. Okay, a into e raised to minus at. A e raised to minus at. Okay. So by observing the function, we know that it is an exponentially decaying function, exponentially decreasing function. Okay, actually this decreases to 0. This function e raised to minus at will decrease to 0 as time t tends to infinity. Okay, hence we can say that the system is stable. Okay, the system is stable. I hope it's clear. Okay, that is by observing the function here. Okay, the observing the function here, we can say that it is an exponentially decaying. Okay, exponentially decaying function. Okay, that is, it is decreases to 0 as time t tends to infinity. Okay, so it is an stable system. Okay, and in the next case, okay, in the next condition, here the function is a by s plus a. Okay, that is the root is, okay, s will be is equal to a. That is, it is located on the right half of S plane. Okay, so that is, if any root of the characteristic equation has a positive real part, this is a positive one. Okay, positive real part, that is lying on the right half of S plane, then impulse response is unbounded. That is, unbounded means it will be infinite. That is, we can say that by observing the impulse response here. Okay, please see here. That is, here the Laplace inverse of a by s minus a, it will be a into e raised to plus at, e raised to plus at. Okay, sorry, a into e raised to plus at. That is, it will be an exponentially increasing function as time t tends to infinity. As time t tends to infinity, the function will be increasing. Always it is increasing. Okay, so the impulse response is unbounded. We can say that the impulse response is unbounded. That is, which is not finite. It is infinite. Okay, so hence we can say that the system is unstable. Okay, so the next case is, suppose if you are having a trans function like that. Okay, m of s equal to a by s plus a plus jb plus something by s plus a minus jb. Okay. Okay, so this trans function, actually this form of trans function we are getting by taking the Laplace transform. Sometimes we will be having a trans function with like that, that is s plus 2 by s square plus 2s plus 3. Okay, so by taking the Laplace, by taking the partial fraction, we can simply, okay, write a trans function as like this. Okay, so if the trans function is in this form, that is, the roots are in complex conjugate, and it is also lying in left half of S-plane. Okay, that is root will be minus a minus jb here, and here minus a plus jb. Okay, minus a minus jb and minus a plus jb if you are taking the roots. So always these are lying on the left half of S-plane. Okay, and if you are taking the impulse response, okay, by taking the Laplace inverse, at last we will get it as 2a into e raised to minus 80, 2a into e raised to minus 80 sine of bt plus 90. Okay, which means the response, impulse response contain a function of sine and e raised to minus 80. E raised to minus 80 means it is an exponentially decaying. So we can say that it is an exponentially decaying sine function. Okay, you can see here. Okay, exponentially decaying. Okay, exponentially decaying sine function. Okay, so we can say that it will reach a value 0. Okay, it will reach a value 0 when time t tends to infinity. Okay, hence we can say that the system is stable here. Okay, so it is decreasing. Okay, it is actually decreasing, not increasing to infinity. Okay, it is always, the amplitude is decreasing, so it is a stable system. Okay, so another example is if you are having a transfer function like this, that is the roots are on right half of S-plane, imaginary roots are on right half of S-plane, that is roots s equal to minus plus a minus jb here, and s equal to plus a plus jb here. Okay, so it will be on right half of S-plane, complex conjugate roots on right half of S-plane. Okay, so while taking the Laplace inverse, we will also get it as 2, at last we will get it as 2a into e raised to 80 sine of bt plus 90 degree. Okay, actually we are getting it as a cos function, and we can simply write it as a sine function like that, that is bt plus 90. Okay, so it will contain characteristics of e raised to 80. E raised to 80 is it is an exponentially increasing function. Okay, and sine. Okay, so we can say that it is an exponentially increasing sine function. Okay, its amplitude will be increases when time t tends to infinity. Okay, so it is an unbounded, the response is unbounded, so we can say that it is an unstable system. Okay, impulse response is exponentially increasing sinusoidal, so it is an unstable system. Okay, so next one is if you are having the roots on imaginary axis, two conjugate roots on imaginary axis, that is here it is s equal to minus jb, here it is s equal to plus jb. So only the imaginary part is there, so it will be on imaginary axis. So if you are taking the Laplace inverse for finding the impulse response, we will get as 2a into sine of bt plus 90, or 2a into cos bt. Okay, so the function will contain only the sinusoidal characteristics. Okay, or cos function. So we can say that the impulse response is oscillatory, that is the amplitude is not changing, because it does not contain any exponential functions like e raised to minus 80 and e raised to plus 80 like that. Okay, if it contains exponential function like that, it will either increase or decrease. Okay, but here only it contains only the cos function or sine function. Okay, so it is an oscillatory response, okay, with a constant amplitude. Okay, always the values, the maximum and minimum values will be constant. Okay, so we can say that it is a marginally stable system. Okay, it will be a marginally stable system. Okay, and next one, listen carefully. Here we are having multiple roots on imaginary axis. Okay, that is pair of roots on imaginary axis, because the function is like that. That is, we will get as minus jb square. Okay, two roots will be on here, and two poles will be on here. Okay, so in that case, if you are taking the Laplace inverse, we will get as m of t will be equal to 2 into 80 into sine bt plus 90. So 80 means it is a ramp function. 80. So the characteristic contains the characteristics of ramp and sine. Okay, ramp and sine. Okay, so the nature will be an ramp. Okay, the impulse response is linearly increasing sinusoidal. We can say that the impulse response m of t is linearly increasing sinusoidal as time t tends to infinity. So in this case also the system is unstable because it is always increasing its amplitude. Okay. And the next case is if you are having a pole at origin, okay, single root at origin. So in that case, the impulse response will be a constant, that is L inverse of A by S will be A. So it will be a constant. Okay, so in that case we can say that the system is marginally stable. Okay, marginally stable. And another case, m of s equal to A by S square, that is two poles are on origin. Okay, so in that case we will get thus AT, m of t is equal to AT. That is, it is a ramp function, linearly increasing ramp function. So it is an unbounded response, that is it will move to infinity as time t tends to infinity. So it is an unstable system. Okay, so these are basically explaining the stability of the system based on the location of poles on S plane. Okay, on S plane. So from that it is clear that if you are having roots, okay, if you are having poles on left half of S plane, if you are having poles on left half of S plane, the system will be stable. And if you are having poles on right half of S plane, okay, like that, right half of S plane, it will be unstable. Okay, and if you are having roots, okay, roots on imaginary axis, okay, pair of only a single pair of roots on imaginary axis, system is marginally stable. Okay, that is in between this stability and instability, that is marginally stable. And if we have multiple roots on imaginary axis, also the system is unstable. Okay, I hope it's clear. So thank you.